Okay, I'll just dive into it. So, hi, I'm Arpita. I'm a final year PhD student working with Professor Bajwa, and I'm going to talk about principal component analysis in IoT systems. So, what's just a brief overview? What's IoT systems? It's a very current thing. We all have devices, and we all are connected with one another through internet. So, and our devices generate a lot of data every second, every millisecond. So, this is a whole big system of integrated devices, and which has the ability to transfer data over a network through which we all are connected. And this typically this Internet of Things infrastructure does not require human to human or human to computer interaction, and mostly AI and machine learning algorithms drive these systems to make sense out of the data. There are multiple applications like healthcare, smart cities, automation, transportation, and so many others. And what basically goes into an IoT system? So there are four main components. There are these devices or sensors that basically collect or generate data, and then there's the connectivity component through which the devices are connected to either a central cloud, or the devices are connected to with each other. And then there's a data processing component, which basically is it means the processing this data generated by these devices. This data processing is usually done in one of the two ways. Either it's centralized, which means all the devices are connected to a central cloud, or it's distributed, which means that there's no central cloud or server, and the devices are connected with each other, communicate with each other, and data is processed locally. And then there's user interface, which is usually like our phones or our smartwatches, through which we see the information and stuff. In this talk, I'm going to focus on distributed processing of data. That's going to be the focus of this talk. So what are these distributed systems? As I already said, they lack a central server. So the devices are connected with each other in the form of an arbitrary network, and they communicate with each other, not with any central cloud. And the devices and hence the devices act on the local information that they have, and also the information that they receive from other connected devices. There are certain advantages of these distributed systems over the centralized ones. First one would be the that it does not have any single point of failure. The cloud in the centralized system, everything is connected to the cloud, so the cloud can be a central point of failure, which does not exist in the distributed systems. It's privacy preserving, because the data is not collated at a single location. So there's the privacy is maintained, like each devices have their own data. Usually raw data is also not exchanged with each other, and there's no communication bottleneck, because with this vast system where there's hundreds of millions of devices and so much data, there can be a communication bottleneck if all the data has to be transferred to a single point. So these are some advantages that distributed systems have over centralized systems. So so that's why we are going to talk about the distributed processing of data. Now, as I said, that because of this huge connectivity of devices, it has led to a concept called big data, which basically means we have a huge volume of data, which is high dimensional, which is generated at a very fast rate, like every seconds. So the volume only keeps increasing. It's heterogeneous, and there are many other characteristics of this big data. But in reality, it's been if examined closely, we usually find that although the raw data can have high dimensions, by that I mean that although a raw data sample can be represented by many features, when examined closely, it's usually found that actually the data samples lie in or near low dimensional spaces, which means that usually a smaller set of features can explain the data very well, and we don't probably need that many features to know the characteristics of the data or data samples. So if we can find those low dimensional spaces, the data would be easier to process. We don't have to process the high number of features that raw data has. And also, if we can learn the features in a way that they're uncorrelated, it helps the downstream machine learning algorithms, which form the crux of uh, all the processing, all the inference algorithms that IoT systems run on. And in some communities that it's also called and disentangled, or but it basically means the same thing. The features are uncorrelated with each other. And we all know that the performance of any machine learning algorithm depends very heavily on we how well the data is represented, how well the data is pre-processed before giving it to a machine learning algorithm. So that's an important, so the data pre-processing step, in a way that we can learn a smaller set of uncorrelated features, is an important pre-processing step. And that's why that's our focus for efficient dimension reduction and uncorrelated feature learning in distributed settings. There are many methods that exist for feature learning. Principal component analysis is a very age-old tool. Low rank matrix factorization, independent component analysis, autoencoders, and many more. In this talk, I'll be focusing on specifically talking about principal component analysis, which does an orthogonal transform, which forms an orthogonal transformation on the data such that the resultant features are uncorrelated. And the work I am going to present also has application in autoencoder training. So I'm briefly going to just touch on that point also later in the talk. So what's a principal component analysis? It's an unsupervised learning technique, which basically it takes a set of raw features that represents a data point, and extracts a smaller set of uncorrelated features that carry maximum information about that data. So mathematically, PCA can be formulated as this formulation shown here, and here the objective uh, basically ensures that the data are represented well. So when the data is projected on some smaller dimension space, it's represented well. So the objective function takes care of the proper representation part, and the constraint takes care of the uncorrelated part. If the off diagonal elements of this matrix are zero, that means that the resultant features, which would be x, if y is a data point and x is the orthogonal basis of the smaller dimensional space that we are trying to find, and if x transpose y is correlation, autocorrelation has zero off diagonal matrices, that means that the resultant features are uncorrelated. It's so the x that satisfies this constraint is actually given by the eigenvectors of the data covariance matrix of sigma. So basically, in short, what we want for PCA is we want to find the eigenvectors of the data covariance matrix, and we want, and that I'll represent with x in whole of my talk, and it will be a k-dimensional. It will represent a k-dimensional space, and k will be much lesser than d, which ultimately means that we get a smaller set of features from the large d set of features. So what's the distributed setup that we are assuming? We assume that we have a connected network of n nodes. It's not fully connected, but it's connected. There's a path from every node to every other node. And I also assume that the underlying graph is undirected, and each node has some samples. So Y is the set of total samples. Let's assume that that's there in the network, and each node has some samples Ni, such that the summation of Ni is equals to n. So this is the setup that we have. representing that this formulation in distributed setting is a bit different. Here, instead of y's, we have yi's because each node has only access to yi's. We don't share raw data, and the constraint is sort of global. So all nodes collectively need to satisfy this constraint because nodes only have yi and x is a kind of a global variable. So all nodes collectively need to satisfy this constraint. So what's our solution for this? So what all do we need for a good distributed algorithm is that we want the algorithm to be computationally inexpensive. We don't want to do too many computations per round. We want a communication efficient algorithm, so such that the nodes do not exchange too many information or do not exchange uh, high dimensional messages between each other. And also we want an algorithm that we can prove mathematically that it converges to the true eigenvectors of the covariance matrix at a fast rate. So that's the focus, and for that our solution is a Krasilina's based method. Krasilina is a stochastic approximation method that was proposed in 1970s. Um, and it was not for a distributed system, and it was proposed for only a single eigenvector, but that's what we used as the base to propose solutions for distributed feature learning, distributed PCA. So what's the solution? The algorithm is called FAST-PCA that I'm going to talk about today. It's called fast and exact distributed PCA. So again, let's talk about this network that we had. We have a network of connected nodes, and let x, I, k, t be the estimate of the kth eigenvector of the data covariance matrix at node I after t iterations. So what happens next? In the next step, when we have these estimates, these estimates are exchanged with the neighbors, only immediate neighbors. So, for example, this the one colored in red is get exchanged to its two neighbors according to the simple graph, and so on and so forth. Next step is taking a weighted sum of these estimates that we get from our neighbors. I'm here showing here only for the third node, but this happens for all the nodes. And these weights are actually decided by the degree of the nodes. So they are pre-calculated weights that come from the degree of the nodes. After this exchange, the update equation. So basically, when we already had the tth estimate, the t plus 1th estimate is basically derived from this equation. Here, the thing to also notice is that there was this communication that happened, and the nodes get the eigenvector estimates of their neighbors, and also it's updated based on its two previous estimates instead of just one. That part was required for an exact convergence to the eigenvectors. The HIKs here are pseudo gradients. We are not using any loss function per se. So these are pseudo gradients that depend only on the local data. So basically, the updates are done based only on the local data and not not the data of any other nodes. Basically, in this pseudo gradient, a part of it is based on Krasilina's rule. As I already mentioned, it was given for only the dominant eigenvector in a stochastic setting, but this pseudo gradient derives motivation from there. And the second part is basically the Gram-Schmidt orthogonalization to ensure that the kth eigenvector is orthogonal to the previous k minus 1 eigenvectors. Also, I would also like to point out that this KIPs are also the estimates. So it's not like that we wait for the previous K minus 1 eigenvectors to estimate the kth eigenvector. All is done simultaneously. All the K eigenvectors are estimated simultaneously. So it's fast in that sense. Also, so to just briefly give the algorithm again, each node receives estimates from its neighbors, takes a weighted average, and then update the weighted combination based on its local information. And this is a working, I'm still working on this theorem, but this is the crux of it, that this algorithm, this FAST-PCA algorithm actually converges at a linear rate to the eigenvectors of the global covariance matrix C, which is basically the covariance is estimated from all the data points, not just the data of any one or two nodes, but all the data points in the network. And it's that's what I'm calling as the global covariance matrix. And we could show that this xik is actually converged to the eigenvectors corresponding to the kth largest eigenvalue of the global covariance matrix. I'm just giving a few experimental results to show the efficacy of the algorithm. So because what we want is not just to estimate the subspaces spanned by the eigenvectors, but exactly the eigenvectors. The error metric I used was where the angles between the estimates and the two eigenvectors qk, I'm denoting here as qk, and the average error is the average across all eigenvectors across all nodes. So for the setup, I simulated a small Erdős-Rényi graph of 10 nodes with a connectivity factor of 0.5, which means that there's there's 0.5 probability that each node will be connected to every other node. And the number of samples, whatever number of samples I generated, I divided it equally amongst the nodes. Also, that although that's not a constraint, like it can be uneven also. And for each experiment, I did 10 Monte Carlo trials because it was synthetic data, and the number of eigenvectors to be estimated I set to 5. So OI is the orthogonal iterations. This is another method for subspace estimation, and it's also shown that in case of distinct eigenvalues, orthogonal iteration also converges to the true eigen values, but orthogonal iteration has an added computational complexity of QR decomposition in every step. So that's there in OI, but that's not there in Krasnodar or FAST-PCA. And I'm showing here plots for two different eigen gaps between the kth and k plus 1 eigenvalues. Here for the setup, again, there were 10 nodes and there were 10,000 samples. So basically each node had only 1,000 samples, and the dimension of the raw data was 20, and the number of eigenvectors I want to estimate is 5. And here we can see that the FAST-PCA algorithm actually matches really closely to the Krasnodar, which is basically a centralized algorithm, which assumes that all the data is available at a single location. And the performance of FAST-PCA and Krasnodar is very close to each other. And I also as I also mentioned that this algorithm, because it's an update-based rule, this has an application on autoencoder training as well. So because that's what autoencoders also do. Autoencoders also compress the data. They also want to find efficient representation of data. So this is a small just prototype experiment for that I did using TensorFlow in Python. That I used the dimension of raw data to be 200, and I took the dimension of the latent layer of the hidden layer to be 10, which basically means that we want to estimate 10 eigenvectors, and the weight matrix would be 100 by 10. and the number of nodes I assumed was again 10 with 100,000 samples, which means that each node had 10,000 samples. And here also we can see that the average error keeps declining. So yeah, that's all I had. These are the few publications that we have on this particular topic, and FAST-PCA's current work that we are doing that I just presented.